we have many things changing. By the way we measure the solar activity, we have many indices. Like, for instance, we have the intensity of the light, the radio flux. We have the irradiance, the total energy that is transmitted per day. We have the sunspots. Sometimes on the sun, you have two black holes. And because they develop magnetic forces, there are areas of the sun that they shine less, okay? So we can have the number of sunspots that decrease the radiance. We also have clouds of flares that they can escape the sun, and these flares can come all the way to the Earth and can be repulsed by the magnetic field, the Earth magnetic field. And there are also corona mass ejections, different types of ejections, which are plasmas that they move in a high velocity. In about 2 days, they reach the top of the atmosphere, the magnetic field, the ionosphere. So there are different indices that, and most of them, they are correlated, but they are not exactly the same.
Can I ask, sorry, Petros, can I ask a question on the previous slide, the one before this? Yeah, so for those Milankovitch cycles, when we're talking about factors which put the Earth's axis into a certain rotation, which leads to a greater likelihood of an ice age, is that only in interactions with the sun, or don't interactions with certain ellipses of planets like Jupiter and Saturn?
Yeah, there is, especially even with the moon, for instance, we have interactions. But in terms of the mass, 99.9 of the mass of our solar system, the sun represents 99.9 of the mass of the solar system. So the stronger forces in the interactions are related to the sun. But yes, there are other interactions with other planets.
Okay, so for only ice ages, it only matters with the sun's gravitational pull, and not like Jupiter isn't big enough to put us into an ice age. Yeah.
Okay. So now the energy balance. So we want to study the climate of the Earth. Of course, depends on how much of light, radiant heat comes from the sun and how much leaves. And it matters also how that energy, radiant energy, will interact with the gas molecules in the atmosphere. So let's first see the energy, the distribution of energy across the different wavelengths that is emitted by the sun. It's throughout the electromagnetic spectrum, the short waves, the gamma and alpha rays that they reach at the top of the atmosphere are here. Then we have X-rays, ultraviolet, and then between 420 and 700 nanometers, we have the visible light, and then we have the infrared light and microwaves and short waves. So we see in this spectrum, and actually this is another way of the magnetic spectrum that you can read. And actually, I will just jump here. Most of the light that comes, that reaches the Earth from the sun is in the visible and near infrared, okay? I'll come back to this again. So some basics, physical, quantum mechanics basis. The first is that an object emits radiance that is related to the thermal energy that that object has, okay? So, and the temperature is a function of the thermal energy. So the larger, the higher the temperature, the more energy that object it will release. And also, the energy that is emitted by that object equals E sigma, which is the Stefan Boltzmann constant, times the square, the fourth power of the temperature of that object expressed in Kelvin. Now, when we talk about the spectrum of energy that is emitted by an object, there are two variables that they are important to know, which one is the energy, the amount of energy, and the second is the distribution of energy. And usually we characterize it by the lambda, the wavelength, the maximum wavelength of that energy, okay? So, you remember from your college that the lower the wavelength, the more the energy is stronger, right? It's okay. So the lower the wavelength, the higher the frequency. So let's say we have an object that has a temperature of T in Kelvin. And you can see from this equation that the higher the T, the more the body is hot, the lower the wavelength. So that means that the spectrum is more energetic, okay? So when we hit an object, the energy shifts to the left. And when we cool an object, the spectrum shifts to the right. So now we have the sun, that has a surface made out of plasma, the photosphere, which is the 400 kilometers thick in the air surface of the sun. And that has a temperature between 4,000 and 6,000 Kelvin. So because of that heat, because of that temperature, the sun emits radiant energy, which we call the solar radiation. And if we go to this formula and we put here 6,000, 4,000, we will end up with something which says that the maximum will be about 400 to 500 nanometers, okay? So if we take an object that has this temperature and we calculate thermodynamically its spectrum, this is what we will see, okay? And this is what we see from the sun. Now, the energy from the sun, we only receive a infinitesimal fraction of the total energy that the sun emits, of course. That energy reaches the Earth, and then the Earth re-emits, and the surface, or the surface of the atmosphere, the average external temperature of the Earth is about 300 Kelvin. And because if it's 300 Kelvin, you can estimate the spectrum of the radiant heat that the Earth will give back, okay? So this is what the sun gives, which is 300, 400, 500 nanometers. And the Earth gives something which is 10,000 nanometers or 10 micrometers. So if you put these two spectra together, here's what the sun gives, and this is what the Earth sends back, okay? So the sun sends short radiation, shorter wave radiation, and the Earth gives longer wave radiation, okay? So as I mentioned to you in the beginning of this class, the atmosphere is not transparent, and indeed the small number of molecules that they are wrapping the Earth is really critical to our lives. And it's critical because it filters the energy that comes in to protect us, but also interacts with the energy that goes out that can have an effect on the Earth and the temperature of the Earth. So as the sun sends short wave, visible to short wave radiation, that radiation enters the atmosphere. And there are two things that the radiation can do with an object. It can be reflected and it can be absorbed. White objects, shiny objects, they reflect the energy. So if you have a mirror and the sun shines, you can reflect that energy. Usually the incident angle equals to the re-emittance angle. And most of the time, not most of them, in principle, there is no loss of energy during the reflection. So it's just a redirection of the energy, okay? So there is no much, the mirror is not going to get very hot, okay? Because it will reflect all energy. The same thing with the snow. The snow reflects all energy. That's the reason when you go to ski, you see people wear masks or they can develop a sunburn. And the reason is because the solar energy that gets from the sun is reflected by the snow that you can be exposed to. So that's the reflection. No loss of energy. Reflection happens on the shiny area, surfaces. The other phenomenon is called absorption. Absorption is the interaction of the solar light with the dark surface, black. In that case, the energy, some of the energy that reaches that surface is absorbed by the surface, and the rest of the energy which is re-emitted from that surface is in longer waves, okay? I meant to tell you for the reflection, the spectrum does not change. So if it's short wave, it will be reflected as short wave. Whereas in the absorption, some of the energy is absorbed and then it gets re-emitted in a long waves in infrared. Okay, so that's a fundamental property of the interactions phenomenon between the interaction of the solar light and the surfaces on the Earth. So clouds, they are white, they will reflect. The ocean is dark, it's going to absorb. Things that they absorb, they get heated, and things which are reflected, they don't really, they remain the same. That's the reason we have the solar panels are black, because we want to absorb the solar energy. So let's say we have a greenhouse and the solar light comes in. Inside the greenhouse, we have dark surfaces or not shiny surfaces, like the leaves, the ground, etc. And the short rays that come from the sun, some of them absorbed and some of them they are reflected. The ones which are absorbed, they shift to the longer waves, infrared, and that infrared cannot really leave out easily the roof of the greenhouse, and as a result, the temperature inside the greenhouse will be higher than the temperature outside. So that's the reason, that's the way the greenhouses work. Short, some of that is absorbed, increases the temperature inside the greenhouse, and the rest goes out. So as I said, the atmosphere absorbs light, and in result, it absorbs light that comes in and comes out. As a result, it keeps the temperature of the Earth around 300 Kelvin, the surface and the atmosphere. Now, we know that there are other planets like the Venus, which has a very dense atmosphere. And because the atmosphere is dense, it withholds more energy. And as a result, the temperature is twice as much as the temperature of the Earth. And the Mars has a very thin atmosphere. And because of the thin atmosphere, the Mars is slightly cooler than the Earth. and much cooler than the Venus. Okay, so that's what the greenhouse effect is. Short radiation, some of that is absorbed, is re-emitted to infrared, and then you